Here are the answers to numbers 29 and 30 from your energy review paper. 29, a 30-gram bullet, which we will be converting to 0.030 kilograms, with a horizontal velocity of 500 meters per second, comes to stop 12 centimeters inside of a solid wall. 12 centimeters, by the way, is 0.12 meters. A, what is the change in the mechanical energy of the bullet? So basically, where did it all go? Well, at the very beginning of the problem, it's not going to have any potential energy. It's going to be all kinetic. At the end of the problem, it's not going to have any potential, and it's not going to have any kinetic because it's sitting inside of a wall. All the energy will have disappeared thanks to thermal energy. So it's all going to go away. And we can figure out how much that thermal energy is going to be, or basically how much energy the system lost, by figuring out, well, how much energy did it have at the beginning? Because at the end, it's going to have no more. And that's just kinetic energy equals 1/2 mv squared. We have the half. The m, as I said, is 0.03 kilograms. And the speed was 500 meters per second. Don't forget to square it. And we know that all the energy is gone. So the change is all of it, which is 3,750 joules, which takes us to part B. What is the magnitude or size of the average force that is exerted from the wall? Well, thermal energy is equal to the force of friction, or the force the wall exerts on the bullet, times the distance that the bullet went into the wall. Well, we just solved for how much thermal energy there is, and we just have to divide by the distance the bullet went into the wall. So that would give us 3,750 joules divided by the 0.12 meters, because we had to convert centimeters to meters, and that gives us a total force that the wall had to exert on the bullet of 31,250 newtons. So that's the average force that it exerted over the 12 centimeters that the bullet went into the wall. That leads us to the very last problem, number 30. A girl whose weight is 267 newtons. That is her weight, not her mass. She slides down a 6.1 meter playground slide that makes an angle of 20 degrees with the horizontal. The coefficient of kinetic friction between the slide and the child is 0.1. A, how much energy is transferred to thermal energy as she's sliding down this thing? Well, thermal energy is equal to force of friction times D. It's a kid who's sitting on a ramp, basically. So the normal force up is going to equal force of gravity perpendicular that goes down into the ramp. So instead of friction, I would write the normal force, and the normal force is equal to the force of gravity perpendicular. So friction is normally mu times the normal force. Here's the mu. And here's what the normal force equals, the cosine of 20 times mg. And the d is just there because that's part of the thermal energy equation. I can now plug in my numbers. The coefficient of friction was given at 0.1, the cosine of 20 degrees times her mass times 9.8, which is just her weight, which was already given in the problem. That's the 267 newtons. And the d is 6.1 meters. And once we do that, we find out that the thermal energy that was taken away thanks to the slide, is 153 joules. Moving on to part B. If the girl starts at the top with a speed of 0.457 meters per second, what is her speed at the bottom of the hill? Well, our initial equation, she does have potential energy because she's at the top of the slide. She does have kinetic energy because it said she has some initial speed. At the end of the problem, she's on the ground, so no potential energy, but she's still moving at the moment that she gets to the bottom of the slide, so she will have kinetic energy. And we already solved for how much thermal energy is getting taken out of the system. So I rewrite my equation without the potential energy 2 in it. This is what I get. Now I have mgh plus 1/2 mv squared equals 1/2 final speed squared plus thermal energy. I'm trying to solve for the final speed, how fast she's going at the end of the slide. So that's v2. So I'm going to subtract thermal energy over, which is why it's minus thermal energy here on the left side. I'm going to have to multiply by 2 or divide by 1/2, and I'm going to have to divide by the mass, and that's why when you see them here, I have the half, I have the m, I divide them over, they hang out in the denominator here, and then of course the square root to get rid of the squared that's hanging out with v. We do not have all of our numbers though. We don't have how high the slide is. We knew the hypotenuse was 6.1, we knew the angle was 20, the problem never gave us the height, so we're definitely going to have to get that. How am I going to do that? I have the hypotenuse. I'm looking for the opposite side. So I'm going to do the sine of 20 degrees equals opposite over hypotenuse. And when I multiply 6.1 over, I get the slide is 2.1 meters high. Also, I don't have the mass of the little girl. Well, force of gravity is 267 newtons. That's her weight. And that equals mg. So I just divide by g, which is 9.8, which I did right here. You can see me plug in the numbers there, and I get that the little girl's mass is 27.2 kilograms. Now I have all the numbers I need. The mass, 27.2 kilograms, G, 9.8, height, 2.1 meters, plus 1/2. The M, again, 27.2 kilograms. The V at the beginning of the problem was given at 0.457 meters per second. Don't forget to square it. Minus the thermal energy, which we solved for in part A, 153 joules. All divided by the 1/2 times her mass again, 27.2 kilograms, and I take the square root. And that tells me that at the bottom of the slide, the little girl is moving 5.5 meters per second.